So limits are one of the first fun things that you get to learn because some limits are very, very easy to calculate, and you can do so in a few seconds. Whereas some other limits can be pretty dang tough. They might take you a very long time. They might involve some very higher mathematics to do, and they range everywhere in between. So you've got to be careful. We're going to start with limits that fall into one of a few different categories. So we've got polynomials, which we're going to take a look at first, and then rational functions, and then finally piecewise functions. So a few different things. Let's start off with polynomials. So polynomials in general are smooth graphs with no holes, asymptotes, or jumps, and they don't have any domain restrictions. Polynomials are really well-defined objects. You can plug in any number from negative infinity to infinity, and you will get something out on the other side. So let's take a look. First off, remember what a polynomial is. A polynomial is a sum or difference of positive integer powers of x. So you're not going to see square roots, you're not going to see rational functions or division, you're not going to see anything squirrely at all, in short. So we're talking x's, x squareds, x to the thirds, possibly constants or numbers all playing together. Now, if you're just taking a limit as x approaching a value, well, that's a pretty well-defined thing. Polynomials are these nice, smooth graphs. So like you shouldn't see any asymptotes or holes or breaks or anything. It's a pretty normal graph, all things considered. So if you want the limit as x approaches a value a of a polynomial, all you're doing is you're taking that value and plugging it into the polynomial. No more, no less. So next up, if you want to take the limit as x goes to infinity, so if you want to take a limit at infinity, then that's going to be plus or minus infinity, and it's going to be determined based on the degree and the lead term of your polynomial. And let's just remind ourselves real quick here, what is degree and what is lead term? So the degree of a polynomial that is the highest exponent that appears. And then the lead term is the number, or some people would call it a coefficient, with that high degree term. And a little smushed. There we go. And we'll see some examples of this here coming up. All right, just in case you didn't memorize and retain absolutely 100% of what you learned in college algebra, that is okay. Just as a reminder here, we've got in behaviors of polynomial functions. So if you have an odd degree polynomial with a positive leading coefficient, so some examples of that might be x cubed, 3x to the fifth plus x squared, anything like that. Your graph is going to go down towards negative infinity as x goes to negative infinity. So as your graph moves to the left, your function goes down, and then as your graph moves to the right, your function moves up. And then for an odd degree polynomial with a negative leading coefficient, it's flipped. So some graphs that would have this property would be negative x cubed, and then maybe like negative 3x to the 7th plus 5x to the 5th. All right, for even degree positive leading coefficients, your graph is going to go up in both directions. Easiest example to think of for that one would be x squared. Another one could be x to the fourth minus x to the third. And I know that we do have some extra terms going on here. So like this and this one. But we don't really care about those terms because with polynomials, the highest degree term pretty much determines the whole polynomial. Those other terms are pretty much meaningless as you're taking x all the way out to infinity or to negative infinity. All right, our last case here is even degree negative leading coefficient. So some examples of graphs with that property might be negative x squared would be the simplest one. And then how about negative 2x to the sixth minus 5x to the fifth plus 3. So let's talk about some of these polynomials. Let's talk about their degree and their lead term just to make sure everybody's on the same base. So I'm going to go through and highlight in green the highest degree term for each one of these. So the highest degree term right here would be that 2. The highest degree term here would be a 6. And then up here, there's our highest degree terms. If you've only got one term, it's not too hard of a decision to make. And then the lead term, this can be an easily overcomplicated thing for some students. So the lead term of a polynomial, we're going to highlight those in, let's use orange. So the lead term is just the number in front of your highest degree term. So for instance, this polynomial down here that I just highlighted, it would have a degree of 6, and it would have a lead term of -2. So let's do a couple more. Over here, hey, we don't have, what's our lead term? It's not there. Oh no. The lead term, if there's not a constant or a coefficient right in front of the term, your lead term would just be 1. So this right here would be a degree 4 polynomial, and it would have a lead term of 1. All right, moving on up to odd degree negative leading coefficient. Highest degree term is a 7 for that one. So it has a lead term of -3. So this polynomial right here would be, here we go, degree 7, and it would have a lead term of -3. And then our last one up here, just to make sure our college algebra is fully reviewed, we would have a lead term of 3 out in front of that term x to the fifth, which is our highest degree term. So this would be degree 5 with a lead term of +3. So that's how you break these down and classify them. So you can do limits at infinity. You can do limits at a number for polynomials. They're pretty agreeable functions. All right, let's try a few of these on for size here. So we've got limit as x goes to 3 of, and all you have to do, you don't have to overthink it, just look at the function that you're trying to take a limit of. This is a polynomial, which means that all we have to do is plug the number in. So we've got 3 times 3 squared minus 2 times 3 plus 4. So that would be 27 minus 6 plus 4, which is 25. And then down here, as x goes to -5, all we do is look at the function. What type of function is it? That's another polynomial. So all we've got to do is plug in -5. So we've got 2 times -5 to the fourth minus 5 times negative 5 squared. So negative 5 to the fourth is 625. And then minus 5 times 5 squared, which is 25. So 2 times 625 is 1250. Then minus 125 would be 1,125. All right, now the one below it, a limit at infinity right here. So all we have to do is identify the degree in the lead term. So the degree of this polynomial, even though we can't see it, if you just have a regular x, it's a degree 1 polynomial. We don't usually call them degree 1 polynomials. We call them lines or linear functions. But so this would be an odd degree and then negative lead term. So if we've got an odd degree polynomial with a negative lead term, the end behavior for that, it goes up to the left and down to the right. So this would be negative infinity because we're taking x to infinity. So we're moving this way. And then as we move that way, our function drops down to negative infinity. And that should make sense because, I mean, what does the graph of that look like? That's just a line with a slope of negative 4 and a y-intercept of positive 3. All right, now the one below it, 3x to the 7th minus 5x to the 4th, that is another odd degree polynomial. But this has a positive lead term. So that means for its in behavior or behavior at infinity, it goes up to the right and down to the left. And we are taking x to go to negative infinity, so we're going this direction down here. So this limit would be negative infinity as well. Let me just highlight our answers here to make it a little bit more clear. There we go. So, hopefully, not too bad.